Hello, and thank you, our colleagues here organizing this webinar. My name is Parisa Aghdam. I represent 6GTandem as a technical lead. Today I want to walk you through a bit of technicalities and also a bit of project view. So I will go straight to the agenda. So on the right-hand side, you see this map representation of the 6GTandem partners. We are from Sweden, Germany, Austria, Belgium, and Switzerland. I want to go through the agenda. First, I will talk about the project overview, a brief introduction to dual band DMIMO concept, and a bit more on why DMIMO, why do we have that in this project. Later, I will discuss about the plastic microwave fiber deployment, a bit on the project's vision and key objectives and technologies addressed in this project. And last but not least, we'll try to address some of the standardization activities that we are aiming to do. So as I mentioned, we are a group of 9 partners, KU11, Infineon, Linköping. I'm from Ericsson. We have Lund, Chalmers, Technikon, and Huber & Suhner. And so the project name is the dual band frequency distributed MIMO approach for future 6G applications. You have the project website. We try to share as much as we can. So if you are interested, please take a look at that. We are also active in Twitter and LinkedIn. We try to share our insights. So this is a stream B0102. What is 6GTandem? Here we try to co-design a novel dual frequency sub 10 gigahertz G-Node B sort of a access point together with the sub terahertz distributed MIMO operation in a new highly integrated and distributed radio transceiver architecture, which we call for radio strike, and through which we try to get to very low energy consumption, high service availability, and low cost of deployment. So we want to address all this through this project. What are the verticals? At this stage, we are really going through what are the use cases, what are the verticals, and we are trying to take information from Reindeer and Hexax, and soon we will draft the first use cases. But we are trying to think of adaptive robotized factories, warehouses, where you have high traffic and densely populated areas, immersive entertainment for a crowd of people, that is arenas, for example, human-machine interactions in care environments, hospitals, and public transportation. So just thought to give you an image to remember 6GTandem, and this is one of those kind of deployments that I just talked about. So you have this you have this purple dot G-Node B access point, through which we try to aim for a good coverage, good resilient coverage, and then we have these blue dots on the ceiling. That is our sub-terahertz D-band deployment through thin, light dielectric fibers. A bit more about the use cases. These are the ones that I just addressed. So you have, we are trying to work our way in two parallel ways, trying to identify the use cases, what the technology does for us. It provides for us low latency. We hope to get sub-centimeter positioning. It's ultra wideband through the D-band sub-terahertz deployment, resiliency through the sub 10 gigahertz access points, computation offloading and front hauling, and we are hoping, for example, if you happen to have an access point there, try to front haul it through radio stripes. So this is one of those things that we are hoping to get and exploring this project. And so what are the possible use cases that we can address, given that we have these possibilities? And so in this slide, I thought maybe I can give you an introduction on this. For example, left-hand side, in 2019 Mobile World Congress, Ericsson introduced this radio stripe concept. It's just a mock-up of a vision that we have in Ericsson, that we hope to be able to have a very light, thin stripe that you have the antenna units, and then you have this daisy chain connection of these low power units. And so here we are in this project. We want to have like a central processing unit where you process all these sub-terahertz generation and reception. You feed the signal RF over this plastic fiber. You have the antenna units connected, as you see in the mid picture. So you have this coupling between the fiber and the antenna. All these areas should be explored and investigated and researched. So to have very low loss connection, for example, here. This is a very simplified illustration of these antenna units. You have these transceiver chains, receive and transmit, and the antenna unit. This is in simplest form. So there is no beamforming I'm talking about here, but it's definitely a possibility. And there we have this embedded wafer level bulk grid array concept, the packaging concept of Infineon, and then a Vivaldi antenna connecting the radio signal towards the plastic microwave fiber. And then on the top right side, we have this very futuristic vision of ours, that you have these antenna units embedded into the fiber. And so it would be an easily deployment. So we know that massive MIMOs having the possibility of beamforming, offering the beamforming possibilities, are the fundamental feature of 5G. And currently we have these centralized solutions, and it's a very great solution, but we are thinking to improve it for certain use cases that I have addressed. So with the co-located or centralized MIMO, you may have service variations. You have very fine beams. There's at millimeter waves, they are sensitive to blocking. Because you have many elements, you have heat concentration, the installations are large and visible, you need radio skilled people to install it, and you have power limitations by SAR. But through the DMIMO deployment, we are trying to take advantage of the co-located MIMO, plus the fact that you will be physically close to the user, trying to reduce the impact of the mentioned issues. Power and backhaul are also integrated into the stripe, and we have this cell-free concept. There is no handover between the cells. There are no plannings required. And so this is on the right-hand side. There is this image of this kind of deployment that I'm talking about. So the reds are the stripes, the fibers. The green crosses, they are representing the antenna processing units. And we have this blue box representing the central processing unit. And this is the sub-terahertz DMIMO deployment. And we have in 6GTandem the sub-10 gigahertz as well, of course. But here I want to talk about these fibers. So what 6G is promising is more than 10 gigabit per second UE throughput, and then we are realizing that it's becoming more challenging in terms of power handling and data exchange. And we see that there is this possibility here. We have this plastic dielectric waveguide to distribute the RF, and at these frequencies, the 140 gigahertz, the dimensions of these fibers become reasonable. And so they are light, you don't, contrary to optical fibers. There are no laser sources required. They're insensitive to temperature variations, and they're wideband compared to coax deployments. So they are like, seems like very niche case here that we can use the fibers. So what is the vision of this project? So the vision is that we try to combine these two deployments, the sub 10 gigahertz and sub-terahertz radio stripe, with antenna placements in the radio stripe by a range of 5 to 20 meters, and trying to reach up to 1 terabit per second in D-MIMO operation. And these are just visions we are talking about. What we want to provide to aim here, there is actually this optimized design of this dual frequency operation. We want to provide ultra high throughput coverage, offload the lower frequency bands, and try to address new services such as high resolution sensing and positioning. So the key objectives are first to develop the 6GTandem system concept driven by use cases. And second is modeling of the 6GTandem system. You need to have these hardware impairment models, especially at sub-terahertz. They are quite needed, and we need to then address these waveforms and communication strategies that sort of optimizes this tandem operation. And then we have to develop the sub-terahertz radio stripe hardware. We need the packaging of the antenna units developed by Infineon. We need to design the chips and so on. And proposing new services enabled by this kind of operation, and the sixth objective is to validate the concept. So what are the key technologies? As I addressed previously, cell-free MIMO, RF-based positioning. We have sub-terahertz packaging technologies based on Infineon's EWLB and sub-terahertz radio stripe. And so last but not least, we have the standardization activities. And so the industrial partners, Ericsson, Infineon, and Hoover and Sooner, will try to address this through their channels, try to identify the standardization gaps and address them adequately. So Ericsson, we have 3GPP core network, 3GPP RAN, the radio and physical layer, specifically the sub-10 gigahertz and sub-terahertz operation will be addressed at regulatory bodies. We have ETSI, ISG, millimeter wave and terahertz specifically, and the 6GIA working groups. Infineon will take their share to contribute to standards as well, and Hoover and Sooner with the IEC standards for radio frequency and fiber optic connector interfaces. And what may lead to standardization, we figure it's the radio interfaces, the D-MIMO, the protocol design for dual frequency operation. And I am done, I guess. That is my last slide.